Pablo is a postdoc here at the Institute, and he's working on neutrinos, neutrino astrophysics, and his talk will be about the diffuse supernova neutrino background. Please. There was one, sorry, before you started, one thing. So sorry that we ran out of coffee this morning. So there's a coffee machine, the espresso machine now, and it might say only for NBIA members. No, you are supposed to use this machine as well. Yeah, just to clarify that. Okay, Pablo, please take it away.
Thank you. First of all, if you want to ask questions, we can wait till the end, or you can interrupt me, whatever you feel more comfortable with. And also, if you want to ask afterwards, just you can write on Slack, or just I will be around, so you can just stop me and we can talk. Okay. But the idea is just to briefly, in this half an hour, like 25 minutes, to introduce what the diffuse supernova neutrino background is, and why this is something you should be excited about, or what I hope you will be excited about as much as I am. So when you think of neutrinos, neutrinos are everywhere, and this is something that is going to be very clear after this school, but we have them ranging in many different energies, from the cosmogenic ones to cosmological ones, that basically are the two extremes. So when you talk about the ones in astrophysics, they mainly come in two families that are kind of independent in a way. There's the high energy neutrinos that come mainly from non-thermal processes, and there's also the thermal neutrinos that are produced for like low energy neutrinos, which are the ones I will be discussing. So I'm going to be focusing on this EB, MEB range of neutrinos. Those are the ones from the sun. On Earth, these are also the ones that are produced in reactors. There are geoneutrinos that also fall in this energy range, and these are also the ones produced in supernova. There will be several other lectures, like invited lectures on supernova neutrinos, but in this case, it's not about single supernova neutrinos, but about diffuse supernova neutrino background. So I want to introduce you to what this diffuse background is, and maybe you have heard that if there is a supernova in the galaxy, then we should observe many neutrinos in our detectors. Those are supernovas that are expected to be around tens of kiloparsecs. And those are, in principle, the rate says we should have a couple of them every 100 years. So the last one was 87A, and then we are still waiting for the next one. It would be nice if it happened during this conference. So no, then we don't have time. I mean, we could reschedule something. Then if you go to further distance to megaparsecs, then you can have roughly a few supernovas every century, but then again, for those, it's so far in distance that we would barely see one neutrino if we see it. And then if you go farther away and then you just look at all the supernova in the observable universe, then for those we have many. We have a few every second. The problem is that we won't see a single neutrino from each of these individual events. However, what the diffuse supernova neutrino background is about observing the diffuse flux coming from all of those supernovas. So not about individual ones, but actually the cumulative flux from all of this past core collapse supernova. So this is what the diffuse supernova neutrino background is. So basically, this short lecture is going to be about how we model this diffuse background, how we try to detect this, and how we are very close to detecting it, and then what can we learn from it. So let me just start with the modeling. This is basically one of the few equations you're going to get in this lecture. So basically, the flux of neutrinos we get from the diffuse supernova neutrino background is related to the emission, that time-integrated emission of each core collapse. And so it depends basically on, in this case, is the mass of the progenitor as a representation of the properties of the core collapse. And then also the energy, which is already, you can see, it has it has been redshifted because we are looking at things that can happen at different redshifts. So we need to take into account the redshift in the energies when we try to model this. It also depends on the supernova population. So how many of these core collapses happen as a function of mass and also as a function of redshift. And then it also needs to take into account the expansion of the universe. And then we integrate over the redshifts that are relevant for observations and of the mass that we know can lead to a core collapse. So let us focus first on the supernova neutrino emission. So you will hear way more about this from Shashank and from Mariam. But basically what happens in the late stages of a high mass star is that you end up forming this onion cell structure with an iron core. And then at some point, this iron core will collapse and form a protoneutron star. And then you would produce, when it reaches nuclear densities, and you produce a shock. So this shock would start disrupting the star, but then it will be, this movement of the shock will be halted, the expansion of the shock. And so you need some mechanism to actually revive this shock, to actually make this explosion to be successful. So if the shock is not revived, then you automatically would end up forming a black hole in a fraction of seconds. If the shock is revived, then you have a successful explosion. And then this is what we call a core collapse supernova explosion. And the remnant can either be a protoneutron star, or if it continues accreting mass, then you end up forming a black hole. So there are many stages here in which it basically that will modify the neutrino emission that we expect from a core collapse. We'll go from either the initial cell structure that we have, the metallicity that we have initially in the star would determine the structure of this free core collapse supernova progenitor. Also, for instance, if it's in a binary system, then mass transfer can also modify this. Then depending on how the shock is revived, there are different mechanisms that can actually revive the shock. It's normally thought to be neutrinos that actually are the neutrino heating, the mechanism responsible for successful supernova explosions, but it could also be magnetorotational instabilities. So all of these things modify the neutrino the properties of the neutrino emission that we expect. So there is a lot in the modeling that enters here, and some of those aspects will be covered by Shashank and Mariam. But just basically, this is one of the astrophysics ingredients that we need to model a diffuse supernova neutrino background. As I said, it's metallicity, binary interactions, how the shock is revived, properties of the neutron star. This can also modify the neutrino emission, the fraction of those core collapses that end up forming a black hole, on how many form a neutron star, how this depends on the initial mass or on the metallicity. All of those things actually are relevant. And then also flavor conversion. So neutrinos change flavor while they propagate. They can also change the way they change flavor while they propagate in matter is slightly different. But in this very dense medium, there are also very high densities of neutrinos. So neutrino-neutrino interactions are relevant. This is a nonlinear phenomenon that is not fully understood in this context anymore, or not yet, at least. And so modeling this is also relevant for modeling the diffuse supernova neutrino background. So there is already a lot of physics involved in this stage. And this actually affects a lot our prediction of what the diffuse supernova neutrino background looks like. This was only one of the ingredients. There's also the supernova population. So basically, the simplest way one can think of how to model the supernova population is to separate the contribution. So how it depends on masses and how it depends on redshift. And then this is just a normalization. So the dependence on masses is what's normally called the initial mass function. And so you assume that stellar masses are distributed according to a certain power law in the universe. That's how likely a star of a certain mass is to be created. And then we also normally assume that the rate of supernovas also follows the star formation history. So you assume that a fraction of the stars that you're forming will end up in a core collapse. This is the simplest way one can actually compute how many supernovas we get as a function of redshift and mass. Of course, you can think of ways in which these two are correlated, and then you can do population synthesis models. So there is a lot of astrophysics also that could modify this simple prescription. So for the initial mass function, normally one just assume this is a distribution of the initial masses that you then evolve, and then you check whether they undergo a core collapse or not. And so a way of doing it is just you take, for instance, you say anything below 8 solar masses would not undergo a core collapse. So you don't care about any of this for modeling the diffuse supernova neutrino background, and then you have all of the other masses. Normally, if you want to do your work based on simulations, you don't have access to thousands of core collapse supernova simulations, so you somehow need to discretize your masses. So for instance, in this case, we had access to 3 different progenitors. So basically, this one forms a neutron star. It's initially 11 solar masses, so we take it characteristic of a certain range of masses. And then we had another heavy one that produces a neutron star as a remnant, and a black hole as a remnant. And so you can, for instance, say in this mass range and in this mass range, it's more likely that you end up producing a black hole. And then in this mass range and this mass range, is more likely that you end up having a neutron star. This is something you need to parameterize based on either simulations or observations or some kind of criteria that you set. And this influences, again, your prediction. And again, this, for instance, 8 solar masses threshold that you set for the minimum progenitor mass that you need to undergo a core collapse can also change depending on, for instance, the mechanism that revives the shock. So there is a lot of astrophysics that can actually influence your prediction. For the star formation rate, so how you assume that the supernova rate evolves as a function of redshift, the easiest way to actually do this is to base yourself on electromagnetic observations of how stars are produced. And this is just a very recent compilation from 2024 of probes of star formation rate density as a function of redshift up to redshift 2 from different bands. And so based on that, then you can probably do some form of fit. And you use that as a proxy for your supernova rate evolution with redshift. Yes, sure.
So here you just show the star formation rate for electromagnetic observations. How about gravitational waves? Do we have observations to find this relation?
You don't get gravitational wave signals from, and that you can use as a proxy for star formation.
Mm-hmm.
If you were to observe gravitational waves from core collapse supernova up to those redshifts, you could, but the gravitational wave emission from core collapse supernova is very weak. So it's very unlikely that you can get up to this redshift. So in this case, it is not a good.
It's not good?
It's not good. I mean, you don't have anything that you can use right now. And I don't think in the near future, you're going to have something that goes far away on the redshift and it's accurate enough so that you can actually use it to infer the redshift evolution of core collapse supernova.
Do you think it's a good way in the far future?
I don't think you have the observational power to actually go that far.
Okay.
Because you need to, I was just about to show it. So you need to go up to redshift 5. And if you...
But at least I can observe a redshift 5 to 10.
With gravitational waves from supernova, you cannot. From binary neutron star mergers, from binary black holes, that is not a problem. But from supernova, the gravitational wave emission from supernova is very weak. It's really, really weak. So the observations you have are very local.
I think so. Okay.
So then you cannot go that far.
Okay, thank you.
But that's a good
question. There will also be a dedicated talk about the gravitational wave aspects. So maybe we can
we can go back to
this
that
again then, yeah.
And then normally you would care about how you model the whole redshift evolution. So the whole supernova evolution as a function, rate evolution as a function of redshift. But then you can see here, so the black line you see here is the total, is this for a particular prediction, but this is the black line is the total DSMB that they get in this model. And then each of the lines is contributions from different ranges of redshift. So you can see the main contributions from the dotted and dashed lines, which are up to redshift 2. So the main contribution from the DSMB basically comes from supernova that happen up to redshift 2. If you want to be accurate, you can extend it up to redshift 5. But anything beyond redshift 5 is really not that relevant. And so basically you can see a little bit far in the, like early in the universe, but not that early. And then the last piece is that you need for modeling is how the universe expanded. And this is actually something that has very little impact in this particular case. First, because as I said, you can only go up to redshift 5. So it's not like you can actually prove, it's not a very deep proof of the universe, but it's also, you have a very large uncertainty here. You saw there's all of these ingredients in the modeling. So this is actually not weighing that much. Actually, people tried to check it. And so this is basically in a very optimistic forecast. They tried to see whether we could measure H0 with a diffuse supernova neutrino background. The diodes line are 1 sigma, 2 sigma, and 3 sigma. It's a very optimistic forecast. And then you can see up to 1 sigma, you can cover, okay, wait, a very large range. And the reason is that you have a very large uncertainty on how many supernovas, the supernova rate, even the local supernova rate is very uncertain. So basically this translates on, if you want to extract something about H0, then this uncertainty just propagates. You could also try to check the equation of state of dark energy, whether like in a very simple model, whether it deviates from -1, and you can fit almost whatever you want. And the reason is the same. You are only sensitive up to redshift basically 2, 5 if you're very optimistic. But again, you saw there are many, many uncertainties. So it's not really a good proof of cosmology. It's just like a nice cross check or like exercise to do. It's not really that relevant. Yeah, sure.
Just keep it.
Okay, so what's the observations here?
This is assuming you observe a DSMB using 20 years of data and the most optimistic setup of detectors you can think of.
I mean, you will to perform K-square statistics. You use here. You use SAM.
They assume this is for a version of hypercamiocan dope with gadolinium using 2 tanks, which is not going to happen. So it is a very, very optimistic setup.
I mean, you use the star formation array observations here to do the K-square statistics. So you also consider the effects of dark energy, but I think the observations, the star formation array is mainly affected by the diameter related physics, not dark energy. And recently, I found that diameter should be dynamical. So here the H0 and H0 you shows is for dark energy. It's lambda CDM model.
This is lambda CDM. This is lambda CDM allowing for an equation of state different from -1. But this is just a background level. So I mean, and because you are not really sensitive either, so because you have a very large uncertainty on the local rate of supernova, so because you have a very large uncertainty on the normalization of this propagates on your normalization of this. So those are basic. I mean, they're clearly degenerate. So if you don't notice, you cannot extract this accurately. Because you don't notice, there's a 40% in here, and at least. So this propagates just here. You cannot extract anything about H0 here. And then because it only goes up to redshift 2, and because there is a very mild dependence on redshift, then you cannot learn anything about redshift evolution of H. Of your Hubble constant. So it's not Hubble constant.
I mean, actually, if we allow diameter has a evolution over time, because recently I found that diameter should be dynamical on cosmic scales. So here, I think if considering a varying diameter equational state, the results will be affected significantly.
I mean, we can talk about it later, but I'm really not sure about it because of this is just up to. I mean, the dominant contributions is at redshift 2, so you really need something to happen at redshift 2 or later, which is not that much time. And then again, you have a very large uncertainty order 40%. So this can mask very many things, and on top of other uncertainties that you have in the model. So just because I wanted to show you, this is the status of DSMB models by 2021. There are more after that. Okay. So you can see there's already basically a 1 order of magnitude band on uncertainty, just because, as I said, there are many different inputs that you can change. And this has been evolving with time, but the landscape of predictions is quite large. And yet we're still getting there. So now we have, I mean, despite all the uncertainties, it's only just roughly 1 order of magnitude that we are talking about. So it's not that bad. We're going to talk about detecting. And the main way to detect is we actually look for electron anti-neutrino component of the flux, and we look for it through inverse theta decay. So electron anti-neutrino interacting with a proton, then you produce a positron that you can either look for Cherenkov light or annihilation with an electron in the medium. And then the neutron, you would expect that it gets captured by a proton producing gammas. And so because this process is not very efficient, this actually has been delaying the detection for a very long time. Now, there was this idea that what if instead of having protons, you could have something else that has a larger cross-section so that it was easier to capture this. And then it's easier to identify this process, because the way we identify this process is you look for the combination of this gammas plus this ones. And you know there is a certain delay time, so you can, and you know the energies, so you can actually look for this specific signal of this energy deposition followed by this energy deposition with a certain time delay. So the idea was to dope water with gadolinium, and this is because this has a much larger neutron capture cross section, so it's way more efficient as a process. And then this is roughly 4.5 MeVs in gammas, and then you have roughly 1 MeVs in gammas here, and then you have a few nanoseconds delay between them. So you can actually look for these coincidences, and that's how you identify this as an electron antineutrino. And because you really need to look for all of these coincidences, you get rid of quite a lot of the backgrounds. So this was the idea for a gadolinium-loaded water Cherenkov, but there are other types of detectors. Ones are liquid scintillators, just as Camland and for Exino. Water Cherenkov, such as Super Kamiokande, or SNO was also water Cherenkov. Now it's a SNO plus. And then now Super Kamiokande got loaded with gadolinium, so it's actually way more sensitive for this diffuse supernova neutrino background searches. In the future, we will have Juno, and then hopefully we will also have Hyper Kamiokande. And it's not clear whether Hyper Kamiokande will be loaded with gadolinium or not. Ideally, it will, but this is uncertain. But basically, this is the landscape in terms of detectors. Where we are, well, this is just limits. So they look at their data and they try to set limits on whether they have an excess over background in their data, and they do it in a spectral independent way. So they look at different energy beams, and this is the limits they extract for Super Kamiokande. So the Super Kamiokande is the red and blue. Blue is what they had after up to phases, so phases 1 up to 4, using only water. And then the red lines are ones they dope with gadolinium in roughly 1 year of 3 years of data. So you can see right now there are some, and well, the gray ones are just this huge band of predictions that I was showing before. So you can see already that Super Kamiokande is excluding some of this many predictions that I was showing. So we are actually, in some cases, touching what we expect. So it's not, maybe detection is not that far, or we are very wrong, which is also exciting. If one actually does a spectral analysis, so instead of just looking for excess over background, you actually input a signal and you try to fit it, and then you find the best fit using both phases of data. You find a best fit that is actually away from 0. It's not consistent with 0 at 2.3 sigma. Again, this is something to be cautious about, because you are inputting some spectral information that you don't know for sure it's true, but it also shows that there is potentially something in the data. So this is this from Neutrino 2024 conference. And then their sensitivity is increasing very fast with time. So maybe this will improve or not, we'll see. But this is, for me at least, this is something to be excited about, because we may be just touching detection. So that's what I said. This is something to be cautiously excited about. In the near future, well, Juno will also start not getting data, publishing data and analyzing data. And so this is basically their sensitivity prospects. So this is, again, this band is just the uncertainty coming from the supernova rate in the modeling. This solid line is just the benchmark they use, and they could get 3 sigmas in a couple of years. So basically, just in a few years, they will also start playing the game. Again, there are uncertainties in the modeling and in their sensitivity studies, but this is also something to be excited about, because it will happen maybe within the span of a PhD or early postdoc. And then a little bit further in the future, there will be Hyper Kamiokande, which just you take Super Kamiokande and multiply by 8 point something. So you accumulate way more statistics faster, which is also nice when you're looking for such a weak signal. There are other detection channels that you could use. So far, it's just based on measuring the electron antineutrino component. But what about the electron neutrinos? Dual, in principle, could do it. They could look for electron neutrino capture on argon. So it's a liquid argon time projection chamber. So it's sensitive to electron neutrino component of the flux. The problem is it's not that large, or it probably won't be that large. And there are very large backgrounds. In this case, because solar neutrino flux is very relevant up to energies around 18 MeV or 20 MeVs, whereas for electron antineutrinos, you can go up to energies of 10 MeVs. So you lose a lot of your region of interest when you look for electron neutrinos, just because there's so many solar neutrinos that you won't see the ones from the DSMV. You're just overwhelmed by them. You could also look for the total flux using coherent elastic neutrino scattering, neutrino nucleus scattering. So this is a neutral current process with a very large cross section that just produces a tiny recoil on a nucleus. So if you observe it, then you're sensitive to the total flux. And in principle, the cross section is pretty large. The problem is you also have very large backgrounds, and then detectors that could be doing this. So the former Darwin and LZ, which now are XLZD, and also res nova, in principle, they are not large enough to actually get enough signal. But let's see how this evolves. But in principle, there are other detection channels that at some point in the future, and I don't know how far in the future, this is to prove the DSMB. And the last part is just what can we learn apart from all the astrophysics and all the detection things that, all the things we would need to learn about the backgrounds to minimize the backgrounds and detector performance to actually get where we get to measure. There's also more physics we can learn from the DSMB, and I'm talking about PSM physics or other neutrino properties. And so neutrinos have masses, and because they have masses, in principle, they could also be unstable, at least two of them. And this means they could decay to lighter states or to other states, depending on your favorite DSM model, book, whatever you like. And so if you want to try whether neutrinos are stable or not, then the ideal setup is in which you go to a very large distance so that they have enough time to decay. And so because they are ultra relativistic, you also need to take into account relativity. And then you want to go to very far distances and ideally to the lowest energy neutrinos that you can. So the actual probe time that they take to propagate is the largest that you can probe. Just to mention, if anyone is actually interested, you don't really get to measure the neutrino lifetime as you could do in cosmology in principle, but you actually get to measure the ratio between the mass and the lifetime. So in principle, all of these terrestrial and astrophysical observations are sensitive to the combination of mass over lifetime. Whereas in cosmology, you could actually prove a different ratio. So book whatever you want. You can think of something that's normally called visible decay, in which you actually observe the decay products. So you get some heavy neutrinos that would decay to a lighter state, and for instance, a photon. That would be a radiative decay. If you have some non-zero magnetic moment, for instance, you can get this kind of decay. Or you can have another portal in which you just don't observe the decay products. Just think of some dark matter or some other mediators, sterile states, whatever you want. How does this affect the DSMB? So because these neutrinos propagate over cosmological distances, then some of them would decay. If the decay is invisible, so think, for instance, we have inverted mass hierarchy, and you say whatever, well, this is not really working, but it's somewhere. Imagine nu2 is just decaying to something you don't observe. Then you take these two lines, and then this is just two different fractions of decay of your flux that decay, and so basically you just expect a reduced flux. That's basically the effect of a decay, is that you will see less flux than you expected. Because there is a large uncertainty, there's this blue band, if you can see, maybe not too much. Because there is a large uncertainty, there is not that much parameter space that you can probe. But in principle, if they decay significantly, you could actually use the DSMB to probe. This is just an example of PSM physics.
So are you sensitive to decay to a lighter state or to an invisible state?
For invisible states, in some cases you are sensitive. It really depends. So if it's nu3, which the one who's actually decaying, you don't really see that, because you're seeing electron neutrinos, and the fraction of nu3s in electron neutrinos, electron antineutrinos, is very small. So nu3 you don't really care. You cannot really probe with the DSMB anything related to nu3, just because the component, the electron fraction of nu3 is very small. So it will just basically fall within your uncertainty. If it's one of the others who decays, either visibly or invisibly, if it decays significantly, you could actually start saying something. Maybe. So the solid lines, this is just two different decay modes, but just for you to see. The solid line is an invisible decay, this dashed line. The dashed line is invisible decay, the solid line is a visible decay of the same state, decaying to different stuff. But again, you see the lines completely overlap. So, you could ideally say, okay, my neutrinos decay. To what did they decay? Well, they decay, that's already a lot to say. So there is a large uncertainty here, not just with the astrophysics, but also within the BSM model that you actually want to probe.
What type of lifetime is?
It's close to the age of the universe. So you really need all of them to decay to actually start saying something. It's very close to the age of the universe. So yes, you could ideally look for BSM signatures in a DSMB, and there are many buts. They're highly degenerate between BSM cases. So you actually, if you can get some additional input from some other long baseline experiments, solar, any other input that you can get is actually going to be useful to break degeneracies, because there are many. It is degenerate with your astrophysical uncertainties in the modeling. So whatever you can, again, use as an input as any electromagnetic constraints that you can have, or if you narrow down this modeling parameter space, then you can actually learn more. And it's also not as significant any signature that you can have, because you have very prominent backgrounds in many cases. So anything that you can do from the experimental side to minimize those backgrounds is also useful to actually learn about the diffuse supernova background. So the overall goal, and this is how I wanted to close this lecture, is we can learn a lot from the diffuse supernova neutrino background. There is a lot of astrophysics. There is a lot that we can learn about the Bohr detectors just by pushing this frontier, and we could probe BSM physics in a way that not many other probes can do. But we have to actually cover the modeling part. We actually need to keep on working on that, because we need to understand better population properties, how they affect our modeling, which are the dominant sources of uncertainties, how the neutrino emission is from core collapse supernova, the different. So there is a lot of astrophysics to learn from there. And there is a lot that we also need to do from the detector side, because, okay, we're targeting this with different techniques, ideally with different detection channels. There are many relevant backgrounds. So any percent efficiency that we can grasp from here, given that we are measuring just a few, DSMB expecting to measure just a few DSMB neutrinos per year, if we can add 1 or 2 per year, this actually makes a big difference. And again, the just overall goal is just to learn. And this is a very unique probe to learn. Thank you very much.
Thank you, Pablo. Are there further questions? There are a couple of. Let's start with the students. Yeah.
So you said in this local population rate, there's this 40% uncertainty, right?
Mm-hmm.
Because there's then also the neutrino emission per supernova. So there's two different models in this sense. The one with the 40%, are we able to by computing more and more actually push this lower? Or is it just pure because we have to wait for more supernovas and otherwise we cannot do anything?
In principle, this part of the uncertainty is going to get narrower and narrower, and there is better roving happening. And so with that, we can actually get a better measurement of the local so there is a very big uncertainty on the local supernova rate. And the reason is there are many, depending on how you look for it, there are many biases. So with a better roving observatory, in principle, this uncertainty can actually be narrowed down quite a bit. I've heard people say 10%. I've heard people said 5%. Let's see. This is something that people know. And then it's also the redshift evolution is something also one should care about. There is also one thing is that when you look for the local supernova rate, you do not see. So you look at the star formation history locally, but then the refraction of those supernova, or when you look at the supernova rate, you see the ones that exploded, but you don't see the unsuccessful explosion. So there are also something called that's the survey of nothing, or it's basically people looking for disappearing stars. It's something that's shining, it's probably a red giant, supergiant, and then they look for it just to disappear. And this would be a signature of a failed collapse. So something that did not manage to explode, but instead just collapsed, forming a black hole. So this is something you also need to correct for in your calculation.
And from such a failed shock, could we still expect a big neutrino flux?
You do get neutrinos. I think they will cover this part. you will still get the neutrinos, but you wouldn't electromagnetically see it as a successful explosion because it's not a successful explosion. So it won't fall when you categorize your data, it won't fall into the category of core collapse supernova that you would use to compute your rate. There are biases.
Thanks for the very wonderful lecture. So I have two questions. The first one is okay, you mentioned about the super K gadolinium docking and we will improve the measurement for the this, but how about like deep core from IceCube? Do they have like a competitive?
They are not in this energy range. So IceCube deep core is sensitive to GeV neutrinos, and this falls in the MEV region. No.
So they cannot like go down to the.
They cannot see these energies.
Okay. The second one will be like so in the axion like community, they talk a lot about like using supernova to probing those kind of particles. So and also like there are also some work like using diffuse supernova to boost the dark matter. Like do you think like all of these will improve the model in here, can also improve the constraint on the kind of work?
In principle, you could think the same. If you have, for people that are not aware, you basically think either dark matter interacting with neutrino kind of model. So basically, you would expect your dark matter produce and interact with your DSMB background. So you would, depending on who's more energetic, one would boost the other. So you would either shift your DSMB to higher energies, or you would heal your higher energies of the DSMB and then boost your dark matter. This will modify the spectrum. The problem with these kind of models is that it normally produces a quite smooth distortion in the spectrum. So it's very likely to be degenerate with some other astrophysical uncertainty. Unless you have some form of absorption that produces dips or peaks in your spectrum, that is a very clear signature. But if it's smooth, if it's something smooth, it's very unlikely to be uniquely observed and attributed to a PSM scenario.
Okay, thanks. Okay, Vivian, one quick question.
Yes, I was just curious. Yes. Can you go back slide one? No, I'm joking. I was just curious about going back to the decay. So one exotic way of explaining the fact that we have not measured neutrino mass is that they've decayed, cosmologically speaking. I'm talking about the cosmology bounds. And in that case, the neutrino lifetime is actually very short in front of the age of the universe. Not like, hundreds of thousands of years, something like maybe millions of years. So my question is then, would you expect not to see anything in neutrino from the supernovae diffuse background, or is there a possibility to cross-check that explanation? Maybe put a bound that would get rid of that explanation as a way to explain the absence of neutrino mass detection.
It depends on how you decay. I mean, are you assuming?
Yeah, I mean, in this case, you're decaying.
They all decay the same way.
They have to decay they have to decay to invisible species. Otherwise, they just hit the minimal mass and that's it.
So they all decay.
Yes.
In that case, you shouldn't. If they all decay invisibly, you shouldn't have a DSMB.
Okay, so
if you don't observe it, that would be.
Hopefully, you guys observe it, and then you can put an interesting bound. Okay.
Okay, let's thank Pablo again.